This is a lecture series on astrodynamics, and to get started, I have some general kick-off material. I don't know to what extent Christoph did similar stuff with you. If you're bored, if you've seen this, just let me know and I'll go faster. If not, then I adapt and paste to what you know, what you don't know. So this is a lecture series in astrodynamics, and it's part of the same class you're doing with Christoph. So it's let's call it a sub-part of space mission engineering and technology. A little bit about myself. I am Nicholas. I am from Luxembourg, and I am currently the CRO of Blue Horizon, which is a startup owned by OHB here in Luxembourg. We mainly deal with space life sciences, so there's a certain focus on life sciences experiments, life sciences payload for ISS, but also for CubeSats. And prior to that, I have been working at some organizations all around the world, in France, in the US, at OHB and at SES, and mainly on topics related to mission engineering, mission design, flight dynamics, and systems engineering. So a little bit the same background than Christoph, but maybe a little more still in astrodynamics, in astromechanics, the movement of bodies through space. Mm-hmm. I don't have yet an email account at uni.lu, but this is hopefully solved soon. And with that, I would actually wanted to do a little roundtable, getting to know you a little bit better. I don't know, maybe we start here, so you shortly tell me who you are and where you're from and what you're interested in and what brought you here in the first.
I'm Michelle. I'm from Michigan originally. I've been here a long time. My background is electrical and computer engineering. I joined the program because I think it's an interesting area and there's a lot of innovation going on. I'd like to apply signal processing and image processing to whatever space solutions I might be involved with. And yeah, I just wanted to update my skill set.
Okay.
Hi, my name is Farzaneh. I'm from Iran. I studied chemical engineering. I have a master's degree in renewable energies engineering. For a while I was working on as a research assistant. I was working on thermal assessment and fluid dynamic devices in MEMSA. And I joined this program as I thought that it's sector that has a lot of space to work on, that is new and promising, and I was interested in space actually.
What region in Iran, if I may ask? What city?
Isfahan, you know?
Isfahan,
yeah. I was studying in Tehran, but I'm working.
Yeah,
I'm Mariusz, I came from Poland. My background is telecommunication and electronics engineering. I was in this military service for Polish Army over 17 years. And so I'm here because from my point of view, is the idea of developing services in satellite business sounds nice, and I suppose, I hope that will be our future. So,
what school have you been in Poland? What school in Poland?
There are several schools. I mean, in military service, also Siberia. The last one was graduated. It was University of Technology in Wrocław in digital telecommunication.
Hello, I'm Vishuddhi Gogoi. I come from India. Prior to this, I was working in the ISRO for 6 years. My background primarily is in the launch vehicle industry because I was working as a project manager there for the launch for the second stage. Prior to coming here for 1 year, I worked with Andrews Corporation, which deals with contract management and transponder leasing. So I just wanted to round my profile basically in the satellite side because I already have a background on the launch vehicle side. So my main motivation was because this course was more based towards the satellites and the industry that is related to satellites. So this is my first master's, so I applied it.
What ISRO center was in the south?
Yeah, I was working in the Vikram Sarabhai Space Center.
Okay.
Stefanos. I come from a mostly research background. I did a general science degree in physics, math, and programming. After that, I did an internship in programming. My main motivation for this master is that I've always wanted to work in space. It started as an interest in astrophysics, but it became more focused on the industrial and engineering side of the space sector, and mostly I've always wanted to do this.
Okay.
Hi, I'm Larry. I worked in a lot of consulting firms, mainly at Accenture and KPMG. First part was on IT development, and the second part was on risk management, developing quantitative models. I have a degree in logistics, bachelor degree in logistics. I'm from Belgium, actually, in Luxembourg since 3 years. Logistics degree with a master in economics and specialization in risk management and quantitative aspects. So I'm more a quantitative person. I'm interested in the master because I think that space industry will develop in the future, and the interest of the satellite and potentially Earth observation aspects.
Okay. Degree in logistics.
Yeah.
That's interesting.
It will be the future as well. The
Yeah.
value chain will be driven by that.
Mm. So you are probably also interested in the interdisciplinary aspect. Of
Yes,
the master
exactly.
mind.
That's really that.
Next one.
Hi, I'm Dave. I'm from Luxembourg. I did my master of my Bachelor of Science in the Netherlands at the Fontis University of Applied Science in mechatronical engineering.
Yeah, by the way, I'm also from Luxembourg.
Yeah.
You know there's a Luxembourger in the room.
Hello, my name is Natalia. I'm from Russia. My background is aircraft engineering. Here in Luxembourg for 2 years, and I was working in financial sector here, but then I found this program, and it's also interesting for me because it's interdisciplinary, and also I would like to continue working with my previous education, let's say. That's why it's interesting for me.
Okay.
Yes.
Good to have you here.
Yeah, thank you.
Hello, my name is Dong Rui. I come from China. I got my bachelor degree in mechanical design and master degree art design in maybe 5 years ago, and it's the first time I study in foreign countries. And I choose this program because I think maybe it will be interesting and new program. You can't find just like this program in other countries.
From what part of China?
Shanghai.
My name is Rod. I come from Brazil. My background is in control and automation engineering. I did 1 additional year in US doing programming. And what brought me here to Luxembourg first was in January this year. I was at IEE, sensors company here of Luxembourg, was working with radar at 24 GHz, 69 GHz too. And what brought me here to the program, like the technical aspect is really exciting, but also I like the management and the interest. Even though I'm from the engineering field, I like the other aspects of the program too, the management business side. Yeah.
Okay. So rather diverse, not everybody is from, say, the hard sciences, so to say. It's rather diverse, that's good. Welcome.
Thank you.
Happy to have you here. Yeah, let's continue. Clicking on the wrong. Yeah, so this is basically, who knows what astrodynamics is, basically? This is, any idea, anybody experienced in that, anybody had courses on that? Well, yeah, so it's something you either love or you hate. And if you're, so I can understand those who don't want to go into it. I mean, it has some, let's say, hard math and physics that is required, but I will try to find a pace that is adapted to, I mean, the general round here. But just to tell you, astrodynamics in general is about trajectories. It's about going from A to B in space. So I'll give you one example of the Rosetta mission. I don't know if anybody knows the Rosetta mission. It's one of the ESA's recent missions, which is going to the comet below, Churyumov-Gerasimenko. It was launched in 2004. And actually, what this course is all about is what is a little bit shown in this ESA video. It's the trajectory, it's how you get there. Meaning at some point you launch a satellite, 12 years through space. So what you will see is a top view of the solar system, and you also see a video that doesn't work.
It's always like that.
Yeah.
Yes, I don't
It
know.
has to do that the video is trying to run on the CPU instead of the graphics.
Yeah, exactly.
Interesting. So you see actually new laws of mechanics, which are not things I wanted to explain today. But the point is you go from A to B, so the Rosetta is this white little arrow, and so there's Earth gravity assists. There is a lot you have to consider from actually going from Earth at the beginning, so there's a rendezvous, you call it with an asteroid called Steins, which is not even the final destination. It goes on and it goes on. The message to take is it goes over for 10 years through space, you finally arrive at that comet there. So there's another rendezvous at another asteroid. It's still not the comet, and now we go further out of the solar system, and there you can see the comet. It's the little white point there. The spacecraft goes into hibernation, and then at some point it arrives. I don't know if anybody knows what happened then once Rosetta arrived at the comet. They actually tried to do a touchdown. There was a little lander, and then this is the comet. The little lander fell on the slope, and the mission actually was not even a real success, in the sense that you could take a few pictures, but that was it simply because the lander didn't land accurately as it should. But that's not, I'm not going to talk about, let's say, landing or touchdown in this course. I could later, but for the moment this video about the trajectory, this funny video that's really not at all showing the real solar system. But anyway, so that's what astrodynamics is about. And yeah. So this is the intended learning outcome I had in mind over the 2 semesters. So what I show in black is what I would like you to learn in semester 1. What I show in blue is what I would like you to learn in semester 2, depending on the pace. Maybe if everybody feels comfortable, I will already do some blue stuff in semester 1, and if it's rather the other way around, I will go slower. I don't know yet today what rhythm we are going to dance. But, so I'm going to read them out, demonstrate a basic knowledge of the principles of satellite orbital mechanics in the limit of the two-body problem, show a basic understanding of analytical orbit integration and numerical orbit propagation, determine an orbit using observations from the ground, demonstrate a working knowledge of calculating orbital maneuvers, have an understanding of basic mission analysis and design, including the design of satellite constellations. Point 5 is very close to what Christophe does anyway, so there might be some overlaps, just let me know if there are. Appreciate the effect of perturbations on the satellite orbit, have an understanding of key approaches taken for the design of interplanetary trajectories, and finally, since Luxembourg did do quite some work in space resources utilization, or since this is a topic that's fashionable in the country, have a general appreciation on how space resources utilization can alter the design of a deep space mission. So this is really about if you get fuel on planet A, how can you use it to go to planet B with maybe having a more economic approach than what you intended in the first time. This is the intended thing. We will see how it goes. By the way, if you have questions, just ask. I don't know if you got the syllabus. It's basically, if Tony showed you the syllabus, but that's...
We have
No, for that one.
So you should get it soon, I guess. That's just what I intend to do in some more detail. Prerequisites, and that's maybe important. So I am assuming, and I'm not sure it is true, that to follow this course properly, it is assumed that during your BSc or sometime in your life, you have attended classes covering the following material. In mathematics, vector analysis, like the simple stuff, simple vector analysis, dot product, cross product, and other basic properties, linear algebra, and in physics, Newtonian basic kinematics dynamics. Please raise your hand if you haven't seen that app. One.
If we haven't seen anything, or
Anything. If this is really something they say, I haven't done it.
Math of
physics,
no.
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 Even elementary.
Elementary, yes, but it's a long time ago.
Mhm. Yeah, since you did stuff in logic. So I'll have to adapt it, it's no problem, but I just need to know it. You?
Mainly the mathematics part I did not have. I had mainly calculus.
You studied what again? I already forgot. What was your background?
Mechatronical engineering.
Okay.
I had some of the dynamics, I guess, but I'm not sure if I really know
Okay.
what it is about.
We'll see how it goes. I mean, if it's too fast for you, just let me know. I guess for some people there shouldn't be any problem, so that's a little bit the challenge that we have in the interdisciplinary way. Let's see it. This is the session plan. Have you seen that? No?
No.
So we are here, October the 3rd, somewhere between 4:30 and 6:15. That's my split up with Christophe, and how I split the course with Christophe. It's worth mentioning that the plan is that all the stuff in blue, that's actually what I'm going to do, and the stuff in black is what Christophe handed in. So that's not what I'm going to talk about. What's interesting to know is that there will always be a lecture series like today where you just get slides and I will present material, and then we do lab works together, so exercises. It's just like you will see these exercises in the beginning, and then we do them together here in a much more laid back way than the presentation of the lectures here. So there's always one lecture and then 2 lab works. One lecture day and then 2 lab works. That's the principle. The lab works is really open book, and we sit there and have a look at the exercises that are handed out. The learning routine, well, basically, you will get the slides, by the way, probably the same chat. I think Maria is.
No, yeah, she can post another.
Yeah, I mean, forget this. It's just this is important. There's a lecture, there's lab work, there's lecture, there's lab work. I mean, some basic principles. Attend the lecture, prepare the lab work session a bit. So I will send out that material prior to the lab works. Then participate in the lab works. Raise questions if you have questions.
So can I ask is astrodynamics the same as orbital mechanics?
Almost to 95%. The difference is orbital mechanics is true even for a planet, or is true for a body that does not have, let's say, a propulsion system like the Moon, Earth, the Sun. They have orbital mechanics. Astrodynamics has this additional idea that you might have propulsion inside. I mean, there's no planets with propulsion inside, but satellites have propulsion inside. They can give a boost, and then they change. That's the difference between orbital mechanics and astrodynamics. In orbital mechanics, we assume that there's no propulsion.
External forces.
Yeah, so during the lab work, the principle is like we will be doing exercises together, and at the end of the session, you give me the exercise of whatever you have done, and I'll collect that. Will be part of your final mark. Evaluation. How's Christophe doing it? I had a discussion with Christophe at some point, but so we agreed at that point. The part for which concerns me is it's 50% the mark during the examination and 50% how actively you participate in the lab works. That basically means be present, try to ask some questions, try to solve some exercises, and hand in your material. How is it with Christophe?
It's not really clear to us.
Yes.
So you could ask him.
Yeah, mostly about the examination, I think.
Yeah.
So for him it's 100%
I think
examination.
it's the same.
No.
Because it's written on Moodle, midterm exam will take place, and it will be 50% of the assessment score.
Yeah, I think the division is the same, just not clear yet, like how the examination will be, if we have like to prepare during the whole semester, or like if
Or even
like how is
So for
it?
me it's very clear actually.
Okay.
You come to the lab box, we do exercise together, you give me your material, I'll take the material with me. That's 50%.
Oh,
The other
okay.
50% is you come to the examination, and the examination is open book. You don't need to learn, you just need to know where you find the stuff that will help you to solve the exercise. The difference between the examination and the lab work is nothing else that in the lab works the exercises will be known to you, I will hand them out, and in the examination they will not be known.
How similar will the exercises be in the exam compared to what we do together?
Very simple. That's why I have another slide in a minute. If you attend the lab works, you will be able to do the examination.
So for the examination, we have all resources available.
All the resources you want to have.
Books,
I'm not sure yet about cell phones. I mean, I'm from a time before cell phones, I don't know, but you can bring whatever book you want to bring or whatever lecture.
Maybe we're buying it now. Maybe we're buying the book now.
If we use PDFs, will we use the computer with internet disabled?
Please say that again.
If we use PDFs, will we use the computer with internet disabled?
If you use
PDF. No, e-books, because mostly they are not. We cannot buy every book, so.
Yeah. I have this is little detail. I mean, for today, I don't see anything that you couldn't use. I mean, you just get some exercise. They will be very similar to what you see in the lab works, and you solve them using the material you have. The one thing you don't know in the examination, what is the exercise? Whereas in the lab works, you will get it on Moodle a few days before.
Okay.
And the level of difficulty of the exercise, I will tune it to how I see how it goes here. Okay? My 3 references I suggest. This is basically also, I brought them with me. This is, let's say, if I don't know, light, medium, heavy. Light is this one, in a sense like this is also the one I structured most part of this lecture. Fundamentals of Astrodynamics, it's a book from the US by Bateman and White. Has been used for the Apollo missions. Simple, compact, and everything you need. And if you just want to pass this course, that's all you need. If you are more ambitious, if you ever think astrodynamics is cool, I want to learn more about it, then it's this one. Bigger, more recent. This is, you can have a look later during the break, Fundamentals of Astrodynamics by Van Laden. This is already, let's say, the one I used during my work. This is the one I used when I studied. This is the one for the pros. This is just the Bible. This is the reference in the domain. This is if you want to be really serious about astrodynamics. That's fundamental introductions to the mathematics and methods of astrodynamics. Okay. What this course will give you, a synthesis of the key textbooks. The absolute minimum needed to get started in astrodynamics. I will try to do the absolute minimum. So just that you get the basic notions of how satellites move in space. For those that are more ambitious, just let me know when we can do, let's say, more funny stuff, but for the moment we keep it simple. Lessons learned from professional experience. Yeah, so I worked in that field for about 10 years, so I did orbit determination and astrodynamics related to space debris. I did LEO orbit, I did LEO, does this ring a bell? Yeah. I did interplanetary trajectories. When I was at NASA, I worked on asteroid rendezvous missions, meaning if you go to an asteroid, how do you want to deflect it whenever it is supposed to hit Earth, stuff like that. So yeah, I'm trying to bring in some lessons learned from there. And I hope to give you an intuition about how objects move in space. That's maybe the most complicated part, because to some extent you need to feel a bit how these objects are moving, and how you can change their path through the solar system or around Earth. Other, what we suggest you to do, attend our session, participate, note everything is on the slides, make notes if you want. The final one is important, focus on the lab works. I mean, all I'm telling you today is basically just input for the exercises. It's all about solving exercises. And then with that, that was my kickoff material and my initial input. Now we will actually start with the first lecture. We have 1 hour, 15 minutes. Let's make a little break in half an hour from now at 5:50, and we do half an hour. So, this is the first of a number of series in astrodynamics. And let's go. So what I'm going to show you is first the historical background, what this is all about, where we are coming from. Then I'm going to show you the general n-body problem, what this actually is, and why it is important. The general n-body problem is nothing else than, let's say, the most general way on how you would phrase, or let's say, set out the arena in which astrodynamics takes place. Then principle of satellite orbital mechanics in the limit of the two-body problem. So we're going from n-body, which means non-specified numbers of bodies in the sky, to two bodies, basically Earth and a satellite. These are the two bodies we're interested in. But initially, when we talk about n-body, the mathematical framework actually takes into account as many objects in space as you want. Then I'm going to end with conic sections. Anybody ever heard or ever seen conic sections? You did? Okay. We'll see how it goes. So, historical background. I mean, these are some people that defined the topic of, you can also call it celestial mechanics for the time being. In history, it started with Aristotle, who was the first guy who actually tried to give a formalized framework of how objects might move in space. He was, of course, saying that the sun was moving around Earth. It was the Earth-centered worldview. And then between Aristotle and Newton, which is basically the main turning point, you had a number of people, and even more, that played a role: Copernicus, Brahe, Galileo, Kepler. Then after Newton, here you have some more: Lambert, Lagrange, Laplace, Gauss, Tsiolkovsky, who Christophe might have told you about the rocket equation. You never heard about it, so you might see that.
Elements?
The Keplerian elements. Yeah, that's actually also what I have in my next, not in this. He showed you the Keplerian elements?
How do you mention presentation?
Mentioned them.
Yes, he mentioned,
Yeah, I'm going
but
to
didn't
go into
explain
details with the
this
Keplerian
inside.
elements, maybe even today, depending on how we make progress. Kepler's laws. So actually now I'm taking out just two historic examples. Who knows about Kepler? Who knows about what his contribution to the field was? So there's actually three laws that Kepler, basically just by intuition, couldn't even prove them, throughout at a given point in time in the early 1600s. Kepler was saying each planet describes an ellipse with the focus at the sun. So K1 is Kepler 1. So on the bottom left you can see what his point was here. You have an ellipse. You have the sun at one focal point. These are the two focal points of an ellipse. And you have a planet going around. That's what he just threw out with a lot of intuition and a lot of data he had from Brahe, another famous astronomer of the time, which he pointed out. The second law is the line joining planet and sun sweeps over equal areas in equal intervals of time. So that's K2 on the bottom right. That means in equal amount of time, so again here you have S is the sun, then you have here the planet. This could be Earth, this could be Mars, and it's true for whatever planet you take. They go around and they actually, in equal amount of time, they sweep equal areas. Meaning between, for instance, time 0 and time 1, takes the equal time from 0 to 1, for instance, between 5 and 6. I don't know, have you seen that? Anybody? Anybody has seen this stuff?
Yes.
Or is this you did?
So even though the distance is farther,
Yeah.
it takes the same amount of time?
Yeah, and that, to recognize it was quite a feat if you're living in the 16th
Yeah.
center.
That's
Yeah.
great.
And I mean, he didn't know why, but he just said, wait a minute, to go from there to there takes the same time than go from there to there. And of course, it has to do with the fact that at one point a planet has to be way faster than at the other. That's why this vector here is much bigger than this one, is a velocity vector. By the way, vectors, that's, I'm getting back to the prerequisites, vector analysis are shown in bold here. Whenever I use bold type, well, the little things in blue here, when you get the handouts, you can read them, there's additional information. But vectors are always shown in blue. Bold, sorry. Then the third law of Kepler, the cube of the mean distance A is proportional to the square of the revolution period P. Which means that if you take A, that's the mean distance, it's from here to here. You divide it, you take it to the cube, and you divide it by the period. The period is the time it takes to make one revolution, that's a constant. So these are three laws of Kepler's. Very famous historical stuff. I just wanted to bring it up.
And what was A?
A, we'll get to it in a, it's actually the distance from the center of the ellipse, which is here, to the border. So I have another figure in a minute. It's called the semi-major axis.
Sir, what's the two questions? How is the second focal point defined on the first diagram?
Say that again?
The second focal point on the first diagram. It seems arbitrarily placed. What is that dot to the left?
It's a good question. Anybody an idea? So indeed, an ellipse, if you do mathematics, an ellipse, if you want to draw it, has two focal points.
Yeah.
In space, all what Kepler was saying is that at one of the two focal points, there's the sun. Your question is what's going on with the other focal point? There's nothing there. It's just, I'm showing it here, but I didn't put an S close to it, which means it is a point in space, but if you went to go there and have a look, there's nothing there. So it's just a mathematical point which in space doesn't exist. So for instance, if you take the practical example, if S is the sun, if P is a planet, any planet in our solar system, let's say it's Earth, where we are on right now, we are going around the sun in an ellipse. Sometimes we are closer to the sun, sometimes we are farther away. But this focal point doesn't exist. It's just a mathematical elite, what do you call it? It's a mathematical point with no physical equivalent.
It's an abstraction.
Yeah, it's an abstraction.
And also, why mean distance and not absolute distance?
Well, when Kepler did these observations, what he did is every evening during, 30 years of his life, he looked at the sky, and he just wrote very meticulously down what he saw. He saw that he did some errors while observing that. So if he actually put his dots, what Kepler actually found was not a line, but he found dots all around, a dot here, dot there, dot here, dot there. And if you draw a line in the middle of it, you find an ellipse. That's why he said that's Kepler's words. He said, on average, that's what I find. Of course, each of my individual points, I'm observing the sky, but not exactly on the ellipse. So after Kepler, we had Newton. Newton, that's just basic physics, has nothing to do with astrodynamics. Who hasn't ever seen Newton's laws of dynamics? Everybody knows that?
I know, but didn't see it.
Being
So-
here long.
So in the same way that Kepler said some stuff, I had Kepler 1, 2, 3, I have now Newton 1, 2, 3. These are just the basic laws of mechanics. Anybody familiar with equations like that? In the Newton 2, the derivative of P is a linear momentum over time. is the same than the derivative of the m times vector v, and it's equal to that. If we are not, well, I think you just have to learn that here. I mean, these are really basics, because at some point later you will get a whole sheet of equations, and we have a problem if we have a problem understanding this. Come and see me if this is a problem. So these are just Newton's laws of motion. Everybody continues in its state of rest or of uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it. The rate of change of momentum is proportional to the force impressed and is in the same direction as the force, with the following equation, just given by Newton in his famous book. To every action, third law, there is always opposite and equal reaction. The little figure on the bottom right-hand side, you see the same. You see a mass. So you see a reference system, x, y, and z. You see a mass placed in the reference system. You see a vector r, which goes from the middle of the reference system to the mass. And you have a sum of force acting on the mass. Just laws of motion. Same Newton's law of gravity. Any two bodies attract one another with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. Again, below you can see the mathematical relation. The force of mass 1, for Fg m1 onto mass 2, so you have mass 1, mass 2, and the force that's acting between them has a negative sign before it, because it goes from m2 onto m1. And it is proportional to the gravitational constant g and the product of m1 and m2 over the radius. Another way to formulate this on the last slide. On this slide, m1 and m2 in the figure on the right hand side are not at the center of the reference frame. Now I'm putting m, a big mass, in the center of the reference frame and a smaller mass outside, a little away at a distance r. And again, we have a similar expression. It's the same expression of the Newtonian force of gravity, but now just with capital M and small m. You can compare them. It's just the same in another way to write it. So this is just historical stuff. This is just Kepler and Newton. Now I'm starting with the general n-body problem, and I wonder if I can do it with you. So, n-bodies, of which body I is a spacecraft. Now, I have again a reference system here with n-bodies. And I'm calling them mi. I goes from 1 to n. So m1, m2, m3, mi, and mn. So I'm putting a lot of little masses everywhere in space. You can picture that like. And now my goal is to study how do these guys attract each other. I mean, I'm still having Newton's law of gravity, and I know that those m1 to mn are probably most likely going to attract each other. So how are they going to move? That's the question here. And so in order to do that, you actually write it out as following. You take here you have an example for body I and body N, how they attract each other, and actually at the end, on the bottom, that's important, so on the last line you get a summation. So everybody familiar with summation signs? Yeah.
Mm-hmm.
Summation from G equals 1 to G equals N of these individual force components. So the total force Fg tot is equal to the sum of the individual forces. And that's the force felt by body I. So the bottom what we have, the equation on the bottom means the force felt on the body I, on the right hand side, is equal to the sum of all the other forces.
The G there, it's
the G stands for gravitational force. F, force gravitational force.
Okay. And in this case, like it's a constant. or no? Depend, because I see like we have like masses of all of them, of all the points,
Yeah.
and distance from
Yeah.
them, and the G is related to what exactly?
The G is just the symbol, the letter G.
Yeah.
You could actually take it out. It just tells us that we're talking about a gravitational force.
Okay,
There's
so
all other kind
okay.
of forces around electric forces. We are not talking about electricity at
Okay,
all.
okay.
We're only talking about one force in this. That's reassuring actually. We're actually just going to talk about one force for most of the time, and that's gravity.
So basically, if you have a program with this equation and you have like the masses and the distances, you can get the final vector where your satellite is going more. Yeah.
If you have a program and you're good at program, this is one, I don't know, this is a very famous computational problem. I don't know if anybody, there's even a science fiction book called The Three-Body Problem. I don't know if you have ever heard of that one. But I think there's no computer has ever solved the n-body problem. Even if you do replace n by 3, it's already damn difficult.
Alright.
They haven't had constellation to satellites operating.
It's approximation. So to solve it is something else than to calculate a reasonable approximation. So solving something mathematically in the equation is one thing. Taking the computers to simplify the problem is something else. So indeed, you're right. If you take a constellation or a collocated satellites, you have n bigger than 3.
Is it because the R is a function of the time?
Yes, it's all because r is a function of time, and we are getting to that equation in a second.
Because it changed so fast, the position and the distances that.
Yeah, I mean, you can at least intuitively get an idea. Imagine you are God for a second, and you put into space a few planets, one there, one there, one there, and one there, and all of a sudden you let loose and you see how they move. They will attract each other, and they will make a very interesting dance, depending on the initial conditions.
Mm-hmm.
And if you change the initial condition, if you take 2, just one here, and you let loose, they will attract each other. That's what we had before. If you have 3, one here, and then put a third one there, this guy will be attracted by that guy, this guy will be attracted by that guy. We have triangular attractions, already more complicated. And here, in the most abstract limit of n could be, I mean, if you take a galaxy has a billion stars, so 10 to the 9th. So n is equal to 10 to the 9th. You cannot solve this with any computer. That's why I'm studying abstract. At the end, be assured I'm going down to n equals 2, where we're just basically having an Earth and a satellite, or the Moon and a satellite, or whatever. But we're starting with the mathematical framework. So I continue. Actually, here now, it's just a consequence of what we have here. So continue this. If we apply Newton 2 to the ith body, we obtain for the equation of motion of the satellite the following. And here we have what you see in what do you call it? Underline encircled with a rectangle. That's the equation. What you were saying a few minutes ago. That's a differential equation. R double dot. Does this? You know what that second derivative? Second derivative of the position vector of body I. That's what that means. R double dot I is the second derivative of the position of body I on, which is on the figure here. R is the position of that guy. Then you have an equation that writes you how to what it actually is. It's F total over mi minus m dot I over mi times r dot I. Where the total force is the gravitational force and other forces in the most general sense could be drag, thrust, solar radiation pressure, perturbation forces, and so on. So this is the most general form of the equation of motion of the ith body in n-body system. It is a second order nonlinear vector differential equation, so you need to know to solve that, and that has defined analytical solution in its present form, which means nobody has ever managed to solve that equation there. That means if we want to continue, we need to simplify. Yes.
Why does it say it's non-linear when all the components are related linearly?
If you have, it is non-linear because on the left-hand side and on the right-hand side you have R. So you cannot find an expression of R that can be isolated.
You want to ask Chris?
No, it's okay.
Because the mass.
Same question.
If you have done launches, you should have done like that.
It's simply because you have the derivative and the initial function in one equation, so therefore it's not
Yeah.
linear.
Even better to say it like that.
I was just going to ask about the mass derivative there, because there's like mass is probably in my mind at least constant, shouldn't change with
On
time.
the next slide. So this is the general form where we assume that the body might change over time its mass.
Okay.
Yeah.
That's actually if the difference between celestial mechanics and astrodynamics. If you have a planet,
Mm-hmm.
you could say that over the times very interesting, it doesn't lose mass.
Compared to the MI, it's like minimal. So like because you're defining by the actual mass, so even if they change, you have some change, but compared to the actual mass of the planet, it's like zero.
And we can even say that over the times we would be studying, you could say that it stays constant. So you're right, m dot I actually implies that in its most general form, this equation has a term where the mass will change.
Mm-hmm.
For a normal planet that we will neglect. But now we're getting back to satellites. Satellites that have a propulsion system, they eject propellant.
Mm-hmm.
And while ejecting propellant, their mass changes.
Mm-hmm.
So if we want to do the most, the equation of motion of a satellite with propellant on board, the m dot I would not vanish. But what I'm going to do for the time being, in the next slide, I'm actually.
And what are the SRB?
Yeah. SRB means solar radiation pressure. These are other forces that could act on, so F tot is the total force, it's the gravity component, Fg, F other. And in theory, so these are all other forces that could act on the body. Let's say for a second it's a satellite, then let's say body I is a satellite. Then Fg tot, its gravitational component, F other is the sum of drag. Drag is what you have if you are going through the atmosphere, like airplanes. You have thrust, that's if you have a propulsion system, you have a thrust in your satellite. SRP is solar radiation pressure, that's an interesting one. That's the photons the sun is ejecting will hit the solar panels of the satellite, and believe it or not, these little photons, I don't know if you've heard about solar sails as a propulsion system. When they're hitting the solar panels, they have a net force and push the satellite.
Mm-hmm.
That's solar radiation pressure, so of course the closer you are to the sun, the more you get it. The farther away you are, the less photons are around, the less you get it. So that's SRP, solar radiation pressure. Then F perturb, that is a general term for other perturbing forces, which is not specified in more detail. But then now we're going to take this equation here and simplify it again. So now to proceed, we simplify by assuming body 1 is Earth and body 2 is an Earth satellite and body 3 to n. By the way, that should be a small m. All the moon, the sun, and other planets of the solar system. The mass of body 2 and all other bodies is constant, so that means this m dot term you were mentioning is going to go away, since I'm going to assume unpowered flight. And F other, this is the one you were mentioning here on the previous slide, I'm going to say it's 0 for the moment. No drag, no thrust, no solar radiation pressure, no perturbation, just the gravitational component. Then we get that equation here, which can be transformed in the one below using what you saw on the previous slide. Then on the bottom, if I replace I by 1, you have the acceleration of Earth. And if you replace I by 2, that's the acceleration of the satellite. You can have a look at that. Then I'm just going to do R12. So on the bottom here we have R1 and R2, double dot, and now I take the difference between the two. That's the distance between the two vectors, which you can see on the figure here. R12. And then you get this final equation on the bottom, which is the equation of the motion of the satellite relative to its central body, and we are going to assume it's Earth. Then you even have that. So R12 double dot, that's the acceleration vector between Earth and the satellite. The left-hand side you have what you call the two-body component because it's for the mass 1 and mass 2. On the right-hand side that's what you call the three or the component to the remaining bodies. Which again I'm going to simplify. So I'm going to take out in a minute the bottom right part, and all we'll have left is that one.
Even we can ignore the effect of move.
Sorry?
Even we can ignore the effect of move.
We cannot, but I'm going to start easy. We cannot. But I thought for the first course I take out the moon, I take out Mars, I take out everything.
The moon is near.
It is damn near, and yeah.
It affects the tides. It affects the tides, so I will
yeah. But I take it out for the moment to have a two-body equation. Earth and the satellite, and the rest we do it later.
No, I'm thinking about the general situation that, for example, we're launching the satellite. We consider which forces we consider the effect of moon or Mars, or
it depends on what you do. If you launch the satellite, I mean, Earth gravity is so predominant that the influence of the moon, I have some nice graphs on that in a later course. You can see that I don't know if it is a million or I don't know if it billion or 10 million times more important than the moon if you launch the satellite. Or if you launch the satellite, you have to fight against Earth's gravity to get out into orbit. At a later time, though, for Christophe, who comes from the geostationary world, if you have a geostationary satellite at 36,000 kilometers from Earth, there, actually, to keep that satellite located at a precise position so that it still feeds the same antenna on Earth. Imagine you have a TV antenna on your home and you have a satellite that feeds it. So there the moon does pull on the satellite, and you have to take that into account. Same as solar radiation pressure, by the way. So if you get to that level of working at SES and trying to keep the satellites where they are, you have to take it into account. I have, in one of the learning outcomes in semester 2, I wanted to talk about that. Yeah. So, as already announced, I'm going to throw away the right-hand one. And I get to the two-body problem. So what you see on the top is basically the exactly same equation than the left-hand side here. And now I continue with that one. I've simplified a lot and I have two bodies. And I'm going to do one further assumption, that is that M1, Earth, I call it now capital M, it's much bigger than M2, meaning the mass of the satellite is negligible with respect to the mass of the central body. And then you end up with the equation on the bottom. R double dot 1, 2 equals minus mu R12 over the norm of vector R12. So the straight line is the norm of a vector to the cube. And mu is nothing else than Gm. That's what you call the parameter of the central body. It's just a way to write it, to win in space. Mu equals G, the gravitational constant of Newton, times M, capital M, the mass of Earth. Then you have that equation. That's the equation we want to solve in the remaining of this first lecture. Even that one is difficult to solve, as you will see, because it's still a differential nonlinear equation. And we're not even going to solve it, but we're just going to approximate. So, constants of motion. The two-body equation of motion is right like that. It's the same equation as we just saw before. And now, actually I'm just going to read out the text. In principle, we want to solve this equation to obtain an expression of r and r dot as a function of time. R is the position, r dot is the time derivative of the position, which is the velocity. You're aware of that? The time derivative. The function. That's what I really want. I want to have the position and the velocity of the satellite. That's actually the goal of this entire lecture. Meaning throughout the whole year, we just want to know the damn position and the damn velocity of the satellite at any time. We want to know where it is and what speed it has. So what I say now, however, this is not so simple as we will see in later sections. This equation there, I mean, don't worry if you struggle Kepler and, yeah, Kepler didn't resolve it either. Newton didn't solve it. I mean, well, Newton did. I think Newton was the first one to solve it. So for the time being, we content ourselves to derive two intermediate results from this equation, which will turn out to be useful in all what follows. We dot multiply and cross multiply. You know what the scalar product and the cross product of vectors are. That'd be good, that'd be helpful. I mean, with that you get R. So what I'm going to do now is I take this equation here, and once I dot multiply it, meaning I take R dot times it, and then later I will cross multiply it. So as you can see here, I start with taking R dot times, I take this, the right hand side to the left hand side, and I multiply it with R dot. And then it's just simple vector operations, but at the end you get to a so-called constant of motion. So here I give you explanations of what you have to do exactly, to give you a little bit of time. If you are still with me that dot multiplying this equation is allowed, and you can do that, then at the end you get the result on the bottom left hand side, which is ordered again, and that's called the specific mechanical energy, also called the energy constant of motion, which is a constant. So what you're basically seeing here on the left hand side is how it is derived. So you finally find that the time derivative is 0, and if the time derivative of something is 0, that means the result, the actual, what you have between the brackets is constant. So what we see here is nothing else that energy is conserved. That you should have seen in principle in physics, even in high school at some point. Energy is conserved, meaning the velocity squared divided by 2 minus mu over r is a constant. Mu, to remind you, is g times m. We saw that just a slide ago. And that's one intermediate result. All I wanted to show is that you can derive that from this two-body equation. You just have to dot multiply it. So you can prove energy conservation by dot multiplying the two-body equation of motion. Then in the same way, by cross multiplying the two-body equation of motion, that's what I'm doing on the right-hand side under 2. You are familiar with the angular momentum. There I proved that angular momentum, which I call h, that's again what is in the bold rectangle, r cross v, position cross velocity, both vectors, is a constant. That's the constant vector h. This is a constant called the specific angular momentum, and since h is constant, it follows that the motion of the satellite is always confined to an orbital plane. Clear that? Motion is in a plane. If I have Earth, I would have need a good Earth and ball. Motion always stays in the same plane around Earth or any other planetary body.
Excuse me, may I just ask again what is exactly mu? Can we just go back 2 slides?
GM.
Maybe next time what I'm going to do is I put the slides on Moodle the day before we do it.
Please.
It's
As soon
good,
as
yeah.
possible, actually.
It's very good. Really,
Even
yes.
on
Follow.
the, yeah, as soon as you can put them up.
Yeah, it's because it's the first one. I have not even access to Moodle yet, otherwise I would have done it. Yeah, mu equals g times n. Which comes again from the previous slide, or it's just linked slide by slide.
We'll use the weekend mostly, I think, for trying to prep the homework.
Okay. Yeah, that's what I'm showing on the bottom. Right here you have Earth, which is capital M. You have your satellite here. You have the position vector, you have the velocity vector, and h, which is the position vector cross the velocity vector is constant. That actually means nothing else that the motion is in the plane. That's just by the intrinsic way how the cross product is defined. And then I define two more angles that will become interesting later, the angle between the velocity vector and the local horizontal, and the angle between the velocity vector and the local vertical. The local vertical is if you look up, it's the point there. Imagine you have a person standing here, the local vertical is there, the local horizontal is perpendicular to it. So it's just two vector angles, phi and gamma. Gamma is the zenith angle and phi is the flight path angle. What is it?
Is it field included?
I can't hear you.
Is it a field included?
No, I wonder what I have to check. Actually, now we would have, so we did the constant of motion here. There's one slide. I'll check what it is. Well, we stand half an hour. Let's do the 5-minute break, and I can fix my own presentation.
Okay, thank you.
We do it like that. So we convene at 6. We do another half an hour. No, we do. Is it 6:30 or 6:15? 6:15. So we do 15 more minutes after 6.
It's 6:15. 6:30, I think. 15? Okay.
Maybe 7.
If you need more time.
No, I have a talk with Christoph. That's what I want to ask. I do.